Okay, let's go ahead and get started. This is class 7. We've got one more proof technique that I want to get through today, and that is proof by induction. And maybe you've seen this before, maybe you haven't, but we're going to go through it anyway today. So let's just get started here. So before we do that, though, before we dig into proof by induction, let's do that one of those proofs by contradiction that I'd mentioned last time. So we want to prove that R plus is not equal to R star using proof by contradiction. And this turns out to be a relatively, I would say, trivial proof. But the reason I'm doing this is that it's a good illustration of how you can use proof by contradiction along with the kind of a counter example. So let's go ahead and do it. So we're going to, first off, like all proofs by contradiction, we're going to start off assuming the negation is true. So R plus not equal to R star is what we're trying to prove. We're going to say, let's assume that R plus is equal to R star. So we're assuming that those two things are equal. We're saying, let's pretend that no matter what regular expression we plug in for R, that these two things are going to always end up being equal. So now we want to say, can we prove that this is false, that this cannot be true? Well, if we can find a counterexample, that'll prove it to be false. We don't have to really, in this case, we can prove that this is just wrong. And if we can prove that that's wrong by finding a single counterexample, then we know it's not true for any language we plug in. So let's see if we can find a counterexample. So we've already made that assumption, R plus is equal to R star. So our counterexample, we're going to plug in A for R, so just the regular expression A, so that just is the symbol A. And we're going to substitute. So rather than R plus equal R star, we have A, which is actually a symbol from an alphabet, A plus equal to R or A star. And by definition of the positive closure and the clean closure, we end up with A plus being that, A star being that. So the only difference being the lambda in the star, no lambda in the A. And you can kind of at this point tell that they're not the same. But let's go ahead and use the justify that those things are now this set and this set are not equivalent. Well, for two sets to be equivalent, and notice I just kind of collapse this, that should be a lambda. And again, I'm going to fix that while I find errors here so we don't wind up with it in the final product. So that should be a lambda. So I just need to change this to change the font. And now we're back. All right. So the only difference being the lambda. So for the two sets to be equal, then one minus the other should be empty set. And if we switch them and do a set difference on them the other way, we should also get the empty set. So if that's true, the only possibility is that this is equal to that. So let's see if that's true. So in our case, though, when we say A plus minus A star, we do get the empty set. So we take everything in A plus, any overlap we take away, that will take away all of them. So that will leave the empty set. But if we switch them around the other way, that leaves behind the set containing just lambda. So we take away all of those in here. There's no lambda in here, so lambda stays in their set there. So that proves that those two things are not equal. And if those two things are not equal, we now have a counterexample. Since we've proven that that proves that that's false. So if A plus equal A star is false, we now have a counterexample that proves that R plus equal R star is false, because when we plugged in an example, that was false, which means that since R plus equal R star is false, that also proves that R plus not equal to R star must be true. So there's our proof by contradiction. So we've proven that R plus is not equal to R star by contradiction. And that proof, like I said, was trivial, but it does illustrate how you can use contradiction, proof by contradiction, along with counterexamples in some cases as a tool. All right, now let's go on to proof by induction. And proof by induction is kind of a special form of proof that helps with dealing with a number of different types of problems or situations. One of them being recursively, there's another misspelling, which cursively. All right. It helps with dealing with recursively defined objects or sequentially ordered systems. And that can make it very useful for kind of algorithmic things, because think of how often in an algorithm you have something that's either sequentially ordered like a iterative, or recursive in nature. Well, like regular expressions themselves are recursive. In all of the composite operators are recursive in some way. Algebra has recursive nature to it. But it's also really useful for automata and languages, as we're going to see later on in the class. So that can be used for proving something. The other useful thing about proof by induction is it can allow you to prove something about a whole range of problems that are all related to each other in some way. And we're going to see that here in just a second. So rather than just a single problem proving that, it allows you to prove things about a family of claims rather than just one single claim for one single example. So let's look at an example. All right, so before we get to the example, let's say that we have some sequence of statements about which we want to prove or make some claims. So here, rather than just one single thing, like before when we did direct proof, we had P, and then we went through this chain of things to prove that Q. Well, here we have more than just P. We've got a whole set of them, P1 through Pn. And we might be able to prove all of these individually, but we want to do a kind of proof that will prove that if P1 is true, then all of these are true. So we'd like it to prove it for all cases. And sometimes you can't do all cases because there might be an infinite number of them. In other words, n could range all the way up to the infinite. So in that case, we couldn't go through and try every one and prove it for each one or test each one. So we want something more powerful that can prove an entire range of statements all at once. And that's where proof by induction really shines. So let's take a look at that. The idea of proof by induction works like this. We're going to prove it for one of those cases individually. Going back, we're going to prove it for one of these. And then we're going to prove we can get from any step n to step n plus 1. And this n here is not the same as this one here, p sub n. It's just we're saying any step that I pick in here, if it's true for that, it also has to be true for the next one. One thing you can do is you can also go take the step backwards. If it's true for this, it's true for the smaller case. It doesn't really matter which way you go in that when you take that in what's called the inductive step. But generally it says go from some n to some n plus 1. And if it holds for n and it also holds for n plus 1, then that's kind of the heart of how induction works. So the idea here is that if we can justify that the claim is true for any n and also true for n plus 1, and we've proven it for just one case individually, then we've proven it for all cases. And the way I like to think about this, we'll talk about in a second, but a couple definitions first. That starting point is called the basis or the base case. The assumption that the claim holds for the sequence is called the inductive assumption or inductive hypothesis. And then the argument that basically takes us from n to n plus 1 is called the inductive step. And that's where the argumentation of the proof is going to come in. And the way I like to think about these inductive proofs is like a ladder. So in other words, the basis proves we can get onto the ladder in some spot. The inductive hypothesis assumes that one rung leads to the next one. The inductive step proves that we can take a step from one rung to the next one. And that we're not talking about a specific rung, we're just saying any rung, taking a step from that one, we can get to the next one after that. And if we can prove that, we can get on the ladder and we can take a step forward on the ladder, then we can get to then we've proven that we can get to any of those positions on the ladder. Hold on one second here. And that's kind of the way that inductive proofs work, is we say, I can prove that this for a base case. I can also prove for any n, I can get to n plus 1, and those logically have to hold true. So therefore, since I can get on there in the base case, then I can get to the next size from the base case, and the next size, and the next size, and the next size. And I can get to any place on that ladder, all infinite of them, even if it's an infinite size of problems. And that's really powerful, because that allows us to prove something for a whole range, even an infinite number of claims, all with this one proof. Okay, let's look at an example. And this example is more mathematical in nature. We're going to look at a second one after we look at this one, which is probably one of my favorite proofs by induction, because it's a little more visual. You can kind of see it in action. But this one, let's go through this first. So we want to prove that integers 1 through n, when summed together, result in n times n plus 1 divided by 2. Or in other words, in more mathematical notation, the sum of I from 1 to n is n times n plus 1 over 2. Now, how do we go about proving that? Well, we're going to use that. And notice this is an infinite number of claims. So we're saying no matter what we plug in for n, we plug in 1 for n, we plug in 100 for n, we plug in 1,000, a million, a billion, anything. There's an infinite number of things we could plug in for n. How do we know it's true for all of them? Well, we could try a few and see, but that doesn't really prove anything about all of them. So we need something a little more powerful. So we're going to use induction. And that's going to allow us to prove this holds true for any value of n, no matter which one we plug in, out of an infinite number of them. And not only that, but we don't even have to know what number, prove it for any of those infinite numbers. We just have to prove it for one and then make that inductive step and prove that. Okay, so let's go ahead and discuss the general form for a proof by induction. And generally you'll have 5 steps. So if you're doing a proof by induction, using proof by induction, you're going to have kind of this 5-step process every time, or you should. There are times where the different steps of this can kind of bleed together into one bigger step, but the idea is you still want to have this. So step 1, we want to state the proposition, what it is we're trying to prove. The next thing we have to do is verify it for the base case, or the basis. In other words, we're going to kind of just brute force solve that and show, hey, it holds true for this base case. And then we're going to state the inductive hypothesis, which is basically going to say, it's kind of like the proposition, but it's tying an n to an n plus 1 in some hypothesis way, or hypothetical way. And then we're going to prove that n is tied to n plus 1 through a sequence of logical steps. And the sequence of logical steps here look more like direct proof when you get to step 4. But we're not doing it in a specific n and a specific. So in other words, proving it for n equal 4 and also n equal 5 does not tie n to n plus 1. You have to keep it kind of abstract using any n leading to the next n plus 1. And then after we've proven that, then we're going to state the conclusion. So let's apply that to our problem. So first off, state the proposition. And the proposition, as we previously stated, is the sum from 1 to n is equal to essentially this sum from 1 to n is equal to, and then our claim is n times n plus 1 over 2. Now, let's verify the base case. So in this case, we'll say, let's put n at 1. So if we put n at 1, the sum from 1 to 1 is just 1. We're just adding 1 plus nothing else. It's just 1. And we're claiming that's equal to, let's plug 1 into this formula here. So we plug 1 in for n. So 1 times 1 plus 1 over 2. So 1 plus 1 is 2. 2 over 2 is 1. 1 times 1 is 1. So 1. So that came out to be 1 is equal to 1. So it worked out in the base case. So we have verified the base case to be true with when we plugged in 1 for n. Now the next step is formulate the inductive hypothesis. And in this case, I'm basically just stating that, okay, a sum from 1 to n looks like we're stating that the hypothesis is we get that. And a sum from 1 to n plus 1, we just plug in n plus 1 for where the n was up here. So n plus 1 goes in for n plus 1 goes in for n. And so now we wind up with this formula. So basically all we've said is that, hey, if we have a sum from 1 to n, we've assumed that it's that. Sum of to 1 to n plus 1, we just plug that in and we get that. So we've got those two formulas there. Now we want to prove that these two things can tie together, where we can get from n plus 1, or n to n plus 1. So to prove that, well, if we look at a sum from 1 to n, it's just 1 plus 2 plus dot 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 plus n. And sum of 1 to n plus 1 is 1 to n, but then 1 more, so there's 1 more n plus 1 added onto the end here. And you can see that there. 1 plus 2 plus 3 plus 4, all the way to n. And then we have just one more than we had up here. And so therefore, it's clear that a sum from 1 to n plus 1, notice that we have 1 through n is already inside of that. So we're just taking 1 through n and we're adding 1 more n plus 1 on the end of that. So that's what this is showing. Sum of 1 to n plus 1 is 1 through n. We just put parentheses around those to group them, plus this n plus 1 at the end. But 1 through n, the sum of those, is what we decided or defined as sum of 1 to n. So now we're just going to take that and plug that in. So in other words, a sum of 1 to n plus 1 is the same as a sum of 1 to n. And then we've just added the n plus 1 on the end of that. So in other words, we've defined n plus 1 as n plus the one more term that we added onto the end of it. And now we've kind of connected, this is what I talked about, connecting the step where we have n to n plus 1. Now we have them kind of together here. We have both the n and n plus 1 all together in this formula. The only difference being sum of 1 to n, we add this, that equals that. Now let's manipulate that a little further. So to prove the inductive step, we need to show that this sum of 1 to n plus 1 is equivalent to or equal to that formula we had earlier in our inductive assumption. This is a little bit different because the n plus 1, I just put it above the 2. It doesn't really matter. If I had it in front of that or up here, we get the same result because it's multiplication. So here's what we have at this stage. So now what we're going to do is we're going to manipulate that a little bit. So let's start off with this sum of 1 to n, or sum from 1 to n plus 1. And remember that that was the same as the sum from 1 to n plus that one extra term, but sum of 1 to n back in our hypothesis was equal to this. This n times n plus 1 over 2. So we have just now plugged that in from our inductive hypothesis. And now what we're going to do is we're going to manipulate this a little bit. And to manipulate this, we want to add these. To add two things, we need a common denominator. So we're going to get a 2 under this by multiplying this term by 2 over 2, which is 1, which isn't going to change it. So we've multiplied that by 2 over 2. And now we have a common denominator of 2. So we can kind of combine these now in the numerator and have them both over 2, which is what we did there. So now we have both of those over 2. And the next step here is now we notice we have this n plus 1 term in both of these. We can factor that out and get n plus 1 multiplied by n plus 2. N plus 1 times n plus 2 over 2. And notice that's what we had on this side over here. We did a little bit of algebra here and said n plus 1 is the same as n plus 2. So we just kind of took away the parentheses and added the ones together to get the 2. But now we have those two things being equal. And since those things are equal, we have now connected n plus 1 to n. So we've proved the inductive step at this point. And I don't know what happened with the quotes here, but I'm going to fix it. Okay, so we've proved the inductive step. And the next step here is state the conclusion as 5. So since we have a basis where n equal 1, which was proven by example, and we prove that we can get from any n to n plus 1 and maintain truth, then that means we've proven it for all n greater than or equal to 1. So thus, sum of 1 to n is always equal to n times n plus 1 divided by 2 for all n greater than or equal to 1. So we've now proven this claim for an infinite number of n by using proof by induction. And that's the end of that proof. Now, rather than stopping there, I like the next example that we're going to look at. We're going to look at one more example today. And this next example is one that I really like because it's visual in nature. And so this is a visual problem. And the visual problem is really slickly solved by proof by induction. So let's take a look at this problem. And again, this is one of my favorite proof by induction examples because it is visual. But the proposition is, given a grid of 2 to the n by 2 to the n cells, with any one cell removed, in other words, one of the cells is destroyed, it's not available to use, it is always possible to tile the grid using 3-cell L-shaped pieces. So in other words, an L-shaped piece would just be 3 of these kind of stuck together like that. And so here's an example. So if we have 2 to the 1 by 2 to the 1, that's a 2 by 2 grid, which we see right here. And then we've destroyed this upper left cell. We just got rid of it. And so if that one's destroyed, I'm coloring the destroyed ones gray here. Then notice we can tile that with an L-shaped piece. So we just put the green as representing that L-shaped piece. We're putting that over those 3. And now we've tiled all of it except for the one that's been destroyed. So it worked for that 2 to 1, single 2 to the 1 by 2 to the 1 case. But let's try it with a different case. So here's the 2 to the 1 case. Here it is 2 to the 2 by 2 to the 2, or 4 by 4. We destroyed one. We picked that one. And then notice here's a tiling that worked for that. We put a green one there. We put so I used different colors to represent those different tiles. And notice so we were able to tile a 2 to the 2 by 2 to the 2 board. And we were able to also do this 2 to the 1 by 2 to the 1 board. But the question is, how can we prove it for all cases? Because notice, just like the last problem, there are an infinite number of options to plug in for n, which can make really large boards. And even in this case, even with a 2 to the 2 by 2 to the 2 board, this 4 by 4 board, we didn't really prove it for all cases. We just said, well, when that one is the one that's destroyed or removed, I can tile it with that. But what about if it's this one or that one or that one or any of them here, this corner one? We would have to prove this, we'd have to go through all 16 possibilities and show you could do it for all of them. Well, even if we do that, well, maybe if you go to like 2 to the, 2 to the 16 by 2 to the 16. So you have this really large, like 65,536 by 65,536. There's a whole lot of things that we'd have to brute force to figure out if that was possible to tile all of them. And we don't really want to do that. We want to know that it's true for all of them. And even if it worked for 2 to the 16, but what if 2 to the, 1024, huge board. You couldn't even write a program necessarily that would go through and solve all of those. So we want to prove it for all cases of n that we plug in for this exponent up here. All right, so let's try one more with 2 to the 2 by 2 to the 2. So here's a 2 to the 2 by 2 to the 2, same square remove we had before. So I try tiling it. I put a green one there, I put the orange one there, put the blue one there, put the yellow one there. And we now have a case where I can't fit a tile and these ones aren't covered. So is that a counterexample? We ended up with a bad tiling when we tried it that time. Is that a counterexample that shows that it can't be done? And the answer to that is no, it's not really a counterexample. We were just stupid in how we placed the tiles on there. Because remember, the claim was that it's possible to do, not that any dumb thing that we try is automatically going to work. So it is possible to tile this. We know that because we just did it back here. There's a tiling with that same one removed. This one actually worked. And so remember the claim. Let's go back one step. The claim was that given a grid of 2 to the n by 2 to the n cells with any one cell removed, it is always possible to tile it, not that every dumb thing we do will result in a tiling. So in this case, this is not a counterexample. We just made poor choices when we placed the tile. So it is possible to tile it. We just did a bad job of it. And how could we have fixed it? Well, put the orange one in the corner, put the blue one here. That would leave these 3 down here for this corner and those 3 for that corner, and we have it done. So keep in mind that if you try to solve something and fail, that doesn't necessarily prove anything. It could just prove you're bad at solving that problem, or maybe not even that you're bad at it. Maybe you just made a mistake somewhere along the way, or made a poor choice along the way. And that's true for this as well. So this is not a counterexample. Okay, so let's dig into the proof. So again, we're going to follow that 5-step process that is generally followed for proof by induction. So number 1, state the proposition. That's what we said earlier. Given a grid of 2 to the n by 2 to the n cells, with one single cell removed, doesn't matter which one, any of them removed, it's possible to tile it using L-shaped pieces where n is greater than or equal to 1. All right, so let's prove it for the base case. The base case, n equal 1, we get a 2 by 2 grid. So 2 to the 1 by 2 to the 1 is 2 by 2. And there's 4 possibilities of which cell can be removed. And notice we could tile each one of those. If we take out the upper left one, we just put the L-shaped piece there. If we take out the lower left one, we put the L-shaped piece there. Lower right looks like this. Upper right Looks like that. So we've now proven for the base case with n equal 1 that all of the boards could be tiled with that. I suppose you could have even proved it with n equals 0 if you wanted to say n greater than or equal to 0, because that would be a 1 by 1 with one cell removed. All of them are covered. All of the available ones are covered because there are no available ones. But in this case, this is a little more fitting with our visual nature of what we want to do this proof. All right, so now moving on, we've proven the base case. Now we want to formulate our inductive hypothesis. And our inductive hypothesis is it's possible to cover a 2 to the n by 2 to the n grid with one square removed. And since that's possible, and we said this is true for any n, we could also say it's also possible to cover the next one size after that, which is 2 to the n plus 1. We can also cover that. So we have made these assumptions. That's our inductive assumption, or our inductive hypothesis is we can cover both this one, and since n plus 1 is just increasing n by 1, it's another n, we can also cover that one. Okay, so now we're going to prove that inductive step. And I apologize for these slides having multiple steps on them without them being broken out, but so kind of ignore what's down here and we'll just go through it. So to prove the inductive step, a 2 to the n plus 1 by 2 to the n plus 1 grid, you can, it has dimensions that are twice that of a 2 to the n by 2 to the n grid, because when we increase the power of 2, we've doubled something. So in other words, if I had a 2 to the 4 by 2 to the 4 grid, that has dimensions that are twice a 2 to the 3 by 2 to the 3 grid. And every time I increase to the next n, I'm doubling the dimension. And that's important. And the reason that's important is because we can think of a 2 to the n plus 1 by 2 to the n plus 1 grid. We can think of that as essentially a square that has 4 2 to the n by 2 to the n grids, because we doubled the size. Think like if you're doubling it, think about it kind of like you're unfolding it to twice the size in both dimensions. So now we have 4 grids instead of where we once had, or a group of 4 of those grids where previously we had 1. If we double it again, we now have 4 of those where previously we had 1. And since one of those 3 boards has to contain the one single cell that was removed, we know that that one can be tiled based upon our inductive hypothesis. So back to our inductive hypothesis, remember it said that one of those cells has one cell removed, and our inductive assumption was that that could be covered. So we know one of those had to contain the single removed cell, so that one can be covered because of this assumption here. Now, what about the remaining 3? Well, the remaining 3 have no cells removed, but we can place a single one of those L-shaped tiles such that it takes 1 square away from each of those ones on the grid. And that means we'll get something that looks like this. So here, the gray cell was the one that was removed. That had to end up in one of the 4 quadrants. And then we're going to take the first tile we lay down and we're going to put it so it touches the other one cell of the other 3. And now notice that because of that, we now have all 4 quadrants are a 2 to the n by 2 to the n grid that have a single cell removed. That one has the original one removed, this one has 1 removed, that one has 1 removed, that one has 1 removed. And according to our inductive hypothesis, we now have 4 grids that are a 2 to the n by 2 to the n with a single cell removed. And according to our inductive hypothesis back here, we know we can cover that. And because we have essentially defined 2 to the n plus 1 by 2 to the n plus 1 as 4 2 to the n by 2 to the n's, we now know that that's true for the 2 to the n plus 1 by 2 to the n plus 1 too. So we've tied the n plus 1 in with the n, and you can kind of see that here in this picture. And so now we've proven that. We've tied the 2 together. So now to state the conclusion, therefore we've proven that a 2 to the n plus 1 by 2 to the n plus 1 grid can always be tiled, since it is effectively just 4 single 2 to the n by 2 to the n grids. And by placing that one tile in the center, it makes them so that it's 4 2 to the n by 2 to the n grids with 1 cell removed from all of them. And we know that can be tiled because of our inductive assumption. So therefore, any 2 to the n by 2 to the n grid can be tiled. And one cool thing about this is notice that this proof also kind of revealed the algorithm for doing the tiling. successfully every time. In other words, take a step back here and look at it, that we find the corner that has the cell removed, we place a tile in the other three, and then we repeat the same process recursively for all of these. So in this one, we'd find the quadrant that has that, leave it alone, put this tile in the corner surrounding that, the other four, and then recursively go dig down and do the next step. And we would do the same thing for all of these. So eventually we would get down to where we're down to our base case, which is just that single 2x2, and we plug in put the tile in whichever orientation surrounds the one that was removed. And we have the whole thing tiled. And that's pretty cool. So here's an example. This is a 32 by 32 grid. And this 32 by 32 grid, notice there's a lot of squares there. And this isn't even that large a grid. We could do 64 by 64, or I don't know, we could do 2 to the 20th and have million by a million. So notice there's a lot of choices for where we'd take one out. So for example, if I were to take out this square here as the one that's removed, how would we tile this? Well, since that's in this upper right quadrant, I'd put the tile down here. And then I would repeat that process for each of those four quadrants. And I divide those up into fours. And where would I put the next one? Maybe here. This one over here would be in that spot. This one down here would be in this spot. And I would repeat that recursively, working my way down through all of the things. Now, as something that's a little bit fun, I went ahead and wrote a little Python script that kind of demonstrates this. Let me just switch over and show that to you here quickly. So I got to switch over to the desktop view, move this so you can see it. Okay, so here's my little Python script that demonstrates this. And notice that this is a 2 to the, or 32 by 32, just like that example that we had on that last page. So notice that you can kind of see the grid behind here. I kind of made the tiles smaller. But what's fun about this is I can click anywhere I want and it'll pick the cell. So I can actually click and hold and drag this around and you can see it performing the tiling. And I kind of color-coded the tiles. The last step ones are that golden color, or brown, or whatever you want to call it. The ones that are the bottom left corners are red, the top left corners are magenta, the lower right is green, and the upper right is blue. But you can kind of see it putting those tiles in no matter what cell I pick, and you can see the algorithm at work. I also made this so you can kind of increase the dimensionality of this up to 256 by 256. And you can kind of still click around in here and see it kind of still tile it. But what's cool about this is we know, I don't know if you can see that on the resolution on the screen. Let me go down a little bit. Maybe you can see that one. But for example, if I click here or there, you can kind of see it change the tiling around wherever I've clicked. But it's interesting because that going through that inductive proof revealed this algorithm to us for how to go about performing the tiling. And there is one other thing that I want to point out about this proof as well, is it also proves something mathematical. And that is that it tells us something about 2 raised to the n times 2 raised to the n minus 1 is always going to be divisible by 3. And notice that that makes sense because notice that we're putting tiles on here that are shaped in 3s. As long as we remove one cell, we can completely cover it without any tile hanging off the edge or without any things uncovered. So that means that 2 to the n times 2 to the n is always going to be divisible by, or minus 1 is always going to be divisible by 3. And that's a pretty interesting thing. One thing that you might want to try is if you write a version of this yourself, I will give you bonus points. So I'll give you 10 bonus points on your midterm if you write a graphical version of this yourself. and I guess I don't really care what language it's in. Just make sure that it goes from the base case, and you can kind of set which cell you want it to tile. There's the 4 possibilities there. And make sure it works for all sizes up to 2 to the 8th by 2 to the 8th. So if you write that, 10 bonus points on your midterm. But you have to write it yourself too. All right, so I'm going to go ahead and stop this program. And I want you to think about, we thought about what the algorithm looked like. That means it'll work for any 2 to the n by 2 to the n grid. One question that to ponder is, what if we have 2 to the n by a 2 to the m grid where they're different dimensions? Is there a way that you could prove or disprove that one? So imagine 2 to the n by 2 to the m. So they're still both powers of 2, but now you can have rectangles. Is it possible to tile any of those with 3 cell L-shaped pieces? Is it possible to tile any of those? And you might think about that and think about, is there a counterexample for that, or could you do a proof by induction for that? But consider that. You know what? For 5 bonus points, if you send me a proof, either proving or disproving that 2 to the n by 2 to the m is either it's always possible or it's not always possible. So prove one or the other of those, and I'll give you 5 bonus points on the midterm. Okay, that's it for today. Everybody stay safe, wash your hands. Next class, we're going to cycle back into talking about formal language stuff. And we're going to look at something that I think is going to be pretty exciting, that we've looked at these regular expressions for defining languages. But what we're going to do next class is we're going to develop these little machines. And what these machines do is they will tell you whether or not a string belongs to a language or it doesn't belong to a language that's defined. So we're going to look at that. And then from there, we're going to move on into looking at some other classes of machines. But we're going to spend a little bit of time on looking at those machines because those are really cool. They're going to tie together with regular expressions and formal languages. So that's what we're going to be doing next class. So that's it. And I will talk to you soon. We probably will not have a quiz next class because we've been talking about all this proof stuff, but we will have one next week. So next class, back to formal languages, and we're going to use some of this proof stuff coming up. That's it.